Okay, I'd like to know, is there, I want to know if there is an absolute maximum on that open interval.
But there's an absolute minimum.
Absolute maximum. Now, just think about it. Don't just hold on for a second. Before you say something, think about it for a second.
Okay.
We got to get some vocabulary straight. It's been a while, but we talked about what we said, that we can take Extrema, the group or the category of Extrema, and we can break that down into a bunch of subcategories. Obviously, we can do Extrema, we can make maxima and minima. But even if we just look at maybe just one or the other of those, let's just deal with maxima for a second. There are different kinds of maxima. You can have a relative maximum, you can have an absolute maximum, or you can have a global maximum, right? And they're all, the meanings are a little bit different. So is there, let's maybe start a little bit easier. Is there a relative maximum on the open interval from A to B?
No. Yes.
How come?
Because there's one point that we can put the highest point in the area.
Okay, good, because there's a peak, right?
Yeah.
Remember, relative maximum is just a peak. What's a relative minimum?
Just a
valley. Yeah, okay. So we do indeed have a relative maximum. We have a relative minimum, okay? Do we have an absolute maximum on that open interval? We do, yeah, and it's the same place, isn't it? Now, what's the definition of an absolute maximum on an interval? Go ahead.
The entire, portion of the thing, not just in that one area, over the whole.
Okay, good. So now we're talking about on the entire interval, is there a point or points that we can, that's kind of bad, we can point to and say that is the highest place on that interval? And we can. It's right there, isn't it? Same place, it's the relative maximum. And the absolute minimum is right there, okay? Does a global maximum or minimum really apply here? Well, it's kind of tough to say. Remember that a global maximum or minimum means on the entire function, regardless of any kind of limits we might have imposed on the domain. So if we're going to take, as an example, if we took a parabola y equals x squared, and even if we're only going to look at this from there to there, if we look at the entire mathematical function, it just goes on forever, right? And for this one, because it's only got one turning point, right, we know that this is the global minimum, right? No matter what we do, that's the global minimum. If this had been, let's just say this had been a piece of a cubic function, and so maybe the thing would have turned like this if we kept going and gone down. Is that a global minimum then? No, it's not. It's not, because we could define a different domain. Like, what if we included the domain that went all the way out to there, for example? Now that's no longer the lowest point, right? So think of it this way. A global extremum is mathematical. It depends on the shape of the entire curve, right? These other things are, they sort of depend on where we're looking, right? A relative extremum is always a peak or a valley, but an absolute extremum depends on the interval in question, right? So the thing that we're going to come out of today being able to do, the big ticket item here, the thing that you're going to be able to do is I'm going to give you a function, and you're going to identify all of the places where, well, all of the absolute extrema, okay, on that interval. That's our goal at the end of the period. Okay, so let's tweak this a little bit here. Let's tweak our picture a little bit. What if we do something like this? Okay, is there a relative maximum on that interval?
Yes.
Yeah, there's a peak. Is there a relative minimum?
No.
No, there is no valley. is there an absolute maximum?
Yes.
Yeah, the highest point. We can see a highest point. Is there an absolute minimum?
Yes.
Yeah.
Yes.
Where?
At the lowest point on the interval.
Because you
So
can't
A.
point to it because you can't
Okay, okay, so here's where our attention is being focused in, right down here, right? We've got this.
Oh, I forgot you had O.
You want to amend your answer, right?
No, there's not,
There's not.
because you can't point to a specific point.
Yeah, you can't point to a specific point, can you? So it's,
Tricky.
if that were a closed interval, yeah, there would be, right? If this endpoint were filled in, if that were filled in, we'd be good. Because then that is the lowest point the end can stand on. But because it's not, filled in, it's not going to work, is it? Right? It's not going to work because there is no point. If I think I've got the lowest point, all I have to do is take a really, really small step to the left along the function, and I'll get another point that's further down, right? This is an open interval, and this is that scenario like if I keep cutting my distance to the door in half forever, I can take steps forever, right? There is no point that I'll get to and be able to say, aha, I'm at the point next to the door. There are an infinite number of points I haven't yet walked over, right? Okay? All right, so let's try something then. Okay, let's take, here's our function. And we're going to look at it on this closed interval. So our goal here is to find the absolute extrema.
And the extremist, the minimum and maximum put together, right?
Right, right. Extreme values, minima and maxima. Before we do this, it just occurred to me that maybe one more thing I should quickly review. What if we had something like this? Okay, where is the absolute maximum on that interval? It's at the peak. Where's the absolute minimum? Ah, okay. At the left endpoint, right?
That doesn't make it out.
What's that?
For the absolute minimum, it doesn't have to be valid.
Right, so this is the first time we've looked at an example today where the absolute maximum or minimum has existed and it has not been a peak or a valley. It doesn't have to though, right? Now what are the two kinds of places where absolute extrema can occur? Okay, it could be, well, okay, yeah, but those highest and lowest points, they could have different characteristics. I mean, they could be, what's one place where an absolute extremum could exist? One kind of place? Peaks. Or valleys. So they could be relative extrema. They could be peaks or valleys, or they could be endpoints, right? Closed endpoints, right? We're talking about now. We're going to look at closed intervals today. So the endpoints will always be closed. So yeah, so those are the only kinds of places where we'd have to check then, right? So what's our strategy going to be when we're trying to find the absolute extrema for this function on this interval? There's only a handful of places. Well, we don't know how many there are specifically, but there's two kinds of places where the absolute extrema could occur. At the endpoints, the x values 0 and 3, right? Or any intervening or interior relative extrema. So any peaks and valleys between the endpoints. Those are the only places we need to check then, right? So what we're going to do is we're just going to build a table that's going to allow us to easily check for those places, or check those values to see which, if any of them, are extrema, right? Okay, so the problem then maybe is the endpoints are easy to find, but how are we gonna find the other x values where the relative extrema, the peaks and valleys occur? Okay, so now remember, there were two kinds of peaks and valleys. This has been like a week ago or close to it. There were two kinds of peaks and valleys that we looked at, right? We said, if this is, here's our function. There's lots of different kinds of peaks and, well, not lots. We've either got rounded peaks, that's a relative maximum, isn't it?
Yeah.
And that's a relative maximum, right? Rounded peaks occur, and smooth peaks occur where we have a horizontal tangent line, right? So notice here, if I draw a tangent line, it looks like that. And so that's a place where the derivative equals 0, right?
Right.
We know that a horizontal line has a slope of 0, right? So those are places where our derivative function have a value of 0. We could have rounded valleys too. That'd be another place where the derivative is equal to 0, right? Now, what's going on in these places though? Sharp corners. That's one of the places we talked about where derivatives are not defined, right? So we could also potentially find we could also find places where the first derivative is undefined, right?
Yeah.
That make sense? Those would also be places where we could have peaks and valleys. Okay, the other thing though is, do they all pan out? So let's look at another example. What if we have something like this?
So what happened to that one example?
Okay. So where are all the places here? I didn't draw this perfectly, but would you agree that these are places with horizontal tangents? There, supposed to be there, and that's it. Okay, so the left one is a place where the derivative was 0. That's a relative extrema. It's a relative maximum, isn't it? Okay. The middle one is a place where the derivative is 0, horizontal tangent. Is it an extremum?
No.
No, it's not. So what's the moral of that story?
It's not, doesn't work all the time.
It doesn't work all the time. Doesn't work all the time, right? So we know that just because we find a place where the derivative function equals 0 doesn't guarantee that it's going to be a peak or a valley. It could be, but it might fail, right? How do we check it?
Plug it
We'll
in.
talk about that.
So like on the right hand one where it's like the slope is 0, like could something tell you that it's not a peak or valley because there's multiple points? Or
Yes, okay, so this question, good question, it's been asked twice. Good question. How do you know if we find a place where the derivative is equal to 0, how do we check to see if it is an extremum? There are two tests, the first derivative test and the second derivative test that we're going to learn. Not today, but we're going to learn them soon. Those are ways for us to determine with, absolutely for certain whether that is a peak or a valley or it failed the test. Now I want to point one more thing out though. Notice that, oops, where did I go? Where's my, I know it's on this page, but it's up higher. Right there. Okay, notice that all peaks and valleys have to occur at places where the derivative is either equal to 0 or undefined. How could you ever possibly define for a continuous function? How could you ever possibly define any other kind of peak or valley? Wouldn't you agree that for a continuous function where my pen never leaves the board, a peak or a valley is either going to be smooth or jagged, right? For sure, right? There's no other possible kind you could draw. And in those two cases, either the derivative must equal 0 or it must be undefined. Okay, so let's combine these two thoughts. Clancy she uncovered the fact here that it doesn't always work, right? So not all of the places where we look are going to pan out, but every place that does pan out, every place where we do uncover a relative extremum must be at a place where either the derivative equals 0 or is undefined.
How do you plug in undefined?
You don't plug in undefined. To find undefined, well, we'll see. We'll have a test for that also, okay?
What the,
Okay? Question?
No.
Okay.
okay.
By the way, what do we call these places? We mentioned this word, but we only mentioned it once.
Critical numbers.
Critical numbers, yeah. The values of x that are potential places where we could have peaks and valleys are called critical numbers, and those are the places where the derivative equals 0 or is undefined. That's how we look for them, but we're going to have to test each one of them, aren't we?
Yeah, we
Okay.
sure are.
All right, so going back to our problem then. What do we probably need to do here if we're going to try to find the relative extrema? In our table, we already know 2 points to check, the endpoints, but we've got to find any critical numbers that lie on that interval, right?
Yay.
Okay, so Jolie, what's our next step?
You need to plug them all. Well, you need to do a derivative.
Okay, we need to differentiate, good. So here's f of x. What's f prime of x going to be?
It would be negative 2x plus 3.
Okay, negative 2x plus 3. So now we're going to look for critical numbers. When we're looking for critical numbers, we have to ask ourselves 2 important questions. Is the derivative 0 anywhere, or is it undefined anywhere, right? So I'm going to make a note of this. Now we have to identify critical numbers. And we ask ourselves 2 questions. F prime of x equals 0. And the answer to that one is?
No. Yeah.
It does. We could set this equal to 0 and get an answer, couldn't we? We could, if I set the derivative equal to 0, negative 2x plus 3 equals 0 when x equals 3 halves, right? Okay.
Wait, isn't it?
So there's one critical number. The other question we have to ask is f prime of x, whether it's undefined. Now, where are the kinds of places, and this is one that, it's a little bit it's stranger in a way. What are the kinds of places where a function could be undefined? What are the 2 things that would have to happen for a function to be undefined? Divide by 0, okay, which would probably amount to a vertical asymptote. So either you have to divide by 0 somewhere for a certain x value, or take an even root of a negative number, right? So we just look at this function here and we ask ourselves, okay, are there any danger zones? Are there any places where there are x's in the denominator? No. Are there any places where I'm taking an even root where an x could cause the argument of the even root to be negative? No. Nowhere, right? It's totally safe. So we can see right here by inspection that none of these exist, right? There are no places where the function could be undefined. And so how many critical numbers do we get?
1.
1. Next question we have to answer is that critical number in our domain?
Yes.
It is. It's on our interval, right? And so now we'll just make our table. Here's how we're going to do the tables. There is no critical number for the undefined. This function is nowhere undefined. Right? We'll look at an example where we do have an undefined, but this one doesn't. Okay, so now we're going to make our table. So our table just looks like this. Here's the x-axis, right? We just want to put the numbers on our table that are the critical numbers. So we have endpoints. We have endpoints at 0, and that's indicating that it's a closed endpoint because I've got the closed bracket, and 3, right? And we've got one critical number in between, which is halfway in between at 3 halves, right? So all we've got to do here is we just have to check the values of the function. We don't have to do anything fancy yet. Pretty soon, we're going to come up with some tests that rely on the first derivative and second derivative to determine what kind of species of critical number is that. Are they extrema, or are they not? Yeah.
Can you scroll up just a little?
Yep, I can.
Walk. Oh, no, nope. You're not.
Okay, so did I Oh, there's our function, negative x squared plus 3x. Okay. So, not quite, not quite. So we're gonna make some rows in our table. Here's an x row. There's f, and then eventually, we're not gonna do this now, but eventually we're gonna add rows for f prime
I don't like that.
and f double prime, okay? And those are the rows that are gonna correspond to the first and second derivative tests, which we'll get to later. But for now, we don't need them. For now, we just need the first two. What are the only places we needed to check? Well, we had our endpoints, right? Which are 0 and 3, and our critical number, which is 3/2. Now, by definition, what is the absolute maximum again? What, I mean, just in general, what is the absolute maximum? Okay, so it's in other words, the highest point on a graph, so it's the greatest value of the function on an interval, right? And the absolute minimum is the least value or the smallest value of the function on an interval, right? Exactly. Now, we know there's only 3 possible places where those extrema can occur, at the endpoints or at the interior critical number, right? So all we have to do here is just check them and compare, right? What's our function? Our function is negative x squared plus 3x. So if we evaluate that at 0, what do we get? 0. Okay, so we get back the value 0. Now, notice here, in this table, notice that this is really an ordered pair, isn't it? Okay? Everybody see that? It's an x and a y value. Okay. What do we get at 3? We plug in 3.
0.
We get 0. Right? I'll go back up.
Oh, at 3.
Okay, yeah.
Okay? And what do we get at 3/2? 3/2, we get what? 3/2, don't we?
Yeah.
Is that right? Yeah. Is that right? 3 times 3? Yeah.
Are you plugging into the original or the?
We're plugging it into the regular function,
I'm
correct?
seeing you look at the derivative, I'm like, it's not following.
No, we get 9/4.
I got 9/4.
9/4, yeah.
Which is the same thing.
No.
Oh.
Okay, so now we can identify
Square root.
where is the, yeah,
I don't get how you got 0 for 3, 0.
It's from the top equation.
because we're just plugging into our function, right?
Oh, I was doing the other one.
Oh, you were doing this one?
Yeah. I was
Okay.
like, what is
You would get 0.
Okay, everybody with me where I got those?
Yeah.
So then where is the relative maximum for our function?
3, 0.
No?
3
Right?
Oh, yeah, because that would just be it.
I mean, did I say relative? I meant absolute.
Yep, you did say it.
Where's the absolute maximum? The absolute maximum occurs right here because of our 3 possible locations. It's the one with the biggest value, right? Okay? Yes?
Didn't we already kind of know there's just gonna be one spot where there's like an x squared? So that
Right. Say it again?
Didn't we already know there's just gonna be like one spot because it's an x squared?
Yeah, we probably did.
Know that, or is that-
Okay, so Clancy's got a good question. She's saying, didn't we kind of know that based on the fact that we've got a negative x squared, so it's turning down, right?
Yeah.
Okay, but the thing we didn't know about this was this parabola is turning down, so was our window gonna be, was it gonna be like somewhere there? Or was it gonna be maybe it was gonna be like somewhere there? I mean, I guess I should have had it right, like right there, right? So we don't know, we didn't know if the endpoints were gonna be the extrema or not. Now, I think maybe saw something kind of impressive here. You saw that because we had 3 points, they probably were gonna turn out that this one was gonna have to be a maximum in this case, right?
Yeah.
Because there's no, I mean, maybe you did, maybe you didn't, but you might have thought about this and said, okay, if this is a parabola, the parabola is only gonna have one place where the derivative is equal to 0, and that's gonna be at the apex, right?
So is that how we can always
Yeah, you can. I think that's a good idea to always kind of look at it and say, okay, does this, now I know, does this make sense? Oh, yeah, it's a parabola, it makes sense. Yeah, yes?
Even though we're given an interval, since we know the equation, could we say that that's the global maximum?
I mean, we could, yeah, we could. All that you're gonna be asked on this assignment is to find the absolute extreme. Okay? Let's do another one.
But what about the last two?
Oh, whoops, did we not, where are the, yeah, I guess I forgot to ask you, where
You said we didn't need those.
the absolute minimum didn't need what?
You said we weren't doing the bottom two.
We're not,
We're doing the minimums.
we're not. But I only asked one question. We found out this was the absolute maximum.
Aren't the other two equal?
Yeah, so what's that mean?
No, relative.
No, they're absolute, they're shared absolute minima, because they both are equally the lowest points, okay?
So, you can just say shared.
Okay, and that sort of works, because I could point at either one of those places and say, okay, that is as low as I could get, right? Okay? How about this one? Okay, that's fine.
It's alright.
Yeah.
I have a weird question, just like a concept.
Okay, listen please.
On the open interval one, when we were talking about how like you can't say the absolute minimum or
Right.
maximum on the open interval, couldn't you just say, like, say it was approaching 3, but it obviously never gets there? Couldn't you say it was like 2.9 repeating? Like, why doesn't that work?
Well, no, because you could say, okay, so you said something there that would work. You could say the limit, right? The limit of x as x approaches 0 from the right would be, except, remember, a limit isn't a number, right? I mean, a limit is, you never actually get
Yeah,
it.
you never get there.
Right.
But, like, so why couldn't you say it was like 2.9 repeating?
Okay, because 2.9 repeating isn't a number. Because whenever you think you've stopped, you've got more numbers to add. You see what I'm saying? It's true. Okay, talk me through this, please. So what are we gonna do? Derivative. What's that give us? 2x to the minus 2, okay? So we don't even really need to necessarily draw a picture for this, right? We just know that we'll eventually, we're gonna kind of work, the way we're gonna go about this, by the time we get to section 3.6, the goal of section 3.6 is just curve sketching. So in section 3.6, you're gonna do something like this. We'll probably take a second derivative also. And then you're gonna, from there, you're gonna build your table all the way down to f double prime, and then below that, you could make a sketch. Okay?
What's the point of taking it as a derivative?
You have no idea at this point. You wouldn't know. But there is. It's gonna be a really slick way, a very efficient, easy way to check to see if they're, what kind of extreme is that coming. No, you're not. Okay, so we gotta ask ourselves though now, we have to look for extrema.
Yep.
So, are there any places where our derivative is what or what?
Yeah. 0, 0.
Okay, equals 0 or undefined. Now look at our derivative here. We get 2x to the negative 1/3 minus 2. So what is x to the minus 1/3?
It's something.
What negative?
Or it's 2x over, or 2 over x to the 1/3.
Yeah, 2 over x to the 1/3, okay? Minus 2, right? Okay, but what I would recommend you do here with this, what I think it's best to do, if you have a derivative that has numerators and denominators, I think it's easiest to just write it as one fraction. So we could multiply the second term by x to the 1/3 over x to the 1/3. Agreed? And we get 2 minus 2 x to the 1/3 over x to the 1/3. If I get a common denominator. Okay. Now this is important here. I want you to tell me, why did we do that? If we're looking for the two kinds of critical numbers we're looking for are places where the derivative is equal to 0 or undefined, why is it especially convenient to have that written as a fraction? Okay. Think about that. While I take roll, you guys think that over. I want an answer here in 30 seconds. Okay, here's my hint. Here's my hint. I want you to think about the behavior of a fraction relative to undefined numbers and numbers equal to 0.
It's easier to tell if it's undefined or not. You can see if it's only a 1 or a 0.
Ah, interesting.
You were right. Sometimes it's used x to the 1/3 so that get rid of the one on the bottom.
Who's missing? Who's missing real quick?
Alex, Lucas.
And Stephanie. Okay, got it. Okay, so what's the answer? What's the answer? Where is it that fractions are equal to 0?
When the bottom, no.
Undefined.
When they cancel each other out.
No.
When-
Say it again. Say it louder. The numerator is 0, right? 0 divided by anything is 0.
Yes.
But if I have a 0 on the bottom, that messes things up. Now, where is it that fractions are undefined?
When the denominator.
I'll translate that for you. When the denominator is 0, right? So, why is it so convenient that this is written as a fraction?
So we can tell if it's undefined or not.
Sure. So we could set up, all we have to do is focus on the numerator. If we want to find out the critical numbers where the derivative is 0, we just take the top of the fraction and set it equal to 0. Okay, so if I solve this, if I solve this equation, all I've got to do is add the second term to the other side, divide by 2, and ultimately what I get is, would you agree? I just get x to the 1/3 equals 1. Oh. To be continued.
Try to explain.